Hello, my name is Thy Lord Root, and welcome to my new tutorial series, An Introduction to C++. Before we get started, I just wanted to cover who should be watching this series. This is mostly designed for newcomers, and so I'm going to be focusing largely on concepts and, when necessary, some practical uses. But, I also hope that it's used for people who have some experience programming as well but haven't learned C++. And if I do a really good job, then perhaps even people who know a little C++ but for some reason or another want a refresher might even find this useful. So that's my target audience. And I also have several goals that I want to fulfill in this series. The first being, of course, that I want to be able to teach newcomers C++. And I also want to drill into the listener these general best practice programming techniques that can help you do it right the first time. And I'm mostly going to be focusing on standard C++. There are some implementation-specific issues that might arise on occasion, and when that happens, I might provide tips for that, but it's not going to be my focus. With that having been said, I have a couple of assumptions that I make. The first is that you have a basic knowledge of computers. I would say that possibly some amount of knowledge akin to what you might learn in a computer literacy class would be sufficient. Certainly any amount of knowledge that you have beyond that would be useful. And I also assume that you're in it for the long haul and that you're willing to do some self-study on the subject as well. So the first question you might have is, what is the C++ thing? And it turns out that it's a high-level multi-paradigm and standardized language. It's high-level because it doesn't directly correspond to machine code, and it's multi-paradigm because it supports multiple coding styles. I'll cover these styles that I have listed here later on as they become more relevant. And it's also standardized because at some point in time a body went out and actually wrote a document that contains a set of rules that compiler vendors can look at, and they can actually write their compiler so that a standardized C++ program can be compiled across vendors and expect to behave the same. There are a few things that C++ is not, and like anything, there are misconceptions. The first is that it's exclusively an object-oriented language, or you can insert your paradigm there, object-oriented being the most common claim for that. And it's true that object-oriented programming is one of the more common uses for C++, but pigeonholing yourself into one particular paradigm is never really that great of an idea, and you really do miss some of the features if you decide that this language only has one way of being used. And it's also not a strict superset of the C programming language. It's also true you can take a vast majority of C programs and compile it under C++ without modification, but in some places the rules are different, and so you can't always depend on that. And while it's intuitively obvious that this isn't the case, in practice we sometimes forget that a C++ compiler can't read your mind, and actually you wouldn't want it to. It would lead to unpredictable code. So with that in mind, here's a basic specification of how intelligent your computer actually is. Is your computer Lieutenant Commander Data from Star Trek? Well, not quite. Your computer is certainly less eloquent, and it only really understands basic expressions. And it also follows your orders to the letter, so in short, your computer's a complete idiot. And this, leads to a discussion about how we used to program before high-level languages existed. or before even assembly languages existed. And when computers were first being developed, you basically worked everything out on paper and converted it into machine code and hoped that you didn't make a mistake in either your conversion to machine code or in inputting the program. And trust me, there were tons of mistakes to be made then. And assembly languages were largely invented to prevent that from happening, and what was nice about it is that machine code now had a symbolic representation, but there were still plenty of errors to be made, and as we can see, there were plenty of faults in either method. The first being that you had extremely verbose code and that it was paced in baby steps, and this often led to several errors, several logical errors in your code. And not only that, but different processor architectures actually spoke different languages. For instance, you could take the x86, which is in most PCs nowadays, or you could take the PowerPC that was formerly in the Macintosh and now primarily used by consoles such as the Wii and the PlayStation 3, and those speak two totally different languages. And so the question then might be, analogous to how two different people from two different cultures would actually communicate with each other. And perhaps the most obvious way is that one learns the language of the other. And this could possibly be described as emulation. It's a little bit easier for a computer to emulate another computer than it is for a computer to understand English for technical reasons that I won't go into. And one of the other ways you could do it is you could actually learn an intermediate language, for instance like Esperanto, and you could communicate in that language. And really the two are more or less the same thing, it's just the application that's different. So we might think of high-level languages as a lingua franca, so to speak. And one of the nice things about high-level languages is that they provide abstractions that we could use to translate what we think into a machine's native language. And this actually has a really cool side effect. You can actually write portable code in a high-level language, which is very useful. And somewhere along the line, if you're a computer science student, you might learn an alternative point of view, which is that there's actually what might be going on is that there's a virtual C++ machine, for instance, that if you really wanted to, you could implement in hardware, although it would be a very painful experience to do that. So you can take a couple of different approaches to translation. Probably the first that we might think of is interpretation, which is basically translating on the fly. So if you go to a foreign country and you try to understand what the citizens of that country are saying in their language as they're speaking it, then that's interpretation. It gets translated at runtime. And so that means that what they say might get translated many times, or if they don't say it, not at all. And this tends to be typical of scripting languages such as Python or Perl. And there's an alternative approach, which is compilation, and that's more like if you're reading foreign literature, perhaps you've had somebody translate it into your language for you, and you actually read the literature in your language as opposed to having to translate it on your own every time you read it. And so languages like C, C++, or Pascal do this. And these aren't the only two approaches. There's also, you actually have a hybrid approach where you can compile down to something that's a little bit easier to translate, and then you can read the so-called bytecode, or sometimes it's called P-code, on the fly and do the translation of that. And languages like Java or C#.NET tend to do this.